The quiz, and let's go over this worksheet. Um, so, all right. The flock of Canada geese is flying south of the winter. On the first day, the geese fly south a distance of 800 kilometers. On the second day, they fly back north 100 kilometers and pause for a couple of days to graze on a sod farm. The last day, they continue their journey south, covering just 750 kilometers. Draw a vector diagram of the journey and find the total displacement. So on the first day, they're going to go south by 800 kilometers. And then the second day, they're going to go north by 100 kilometers. And then on the third day, they're going to go back south 750 kilometers. So they want a vector diagram, so that's kind of what a vector diagram would look like. If you really want to get technical, these would all be collinear, but I don't think it's going to look very nice because they would all be on top of each other. But technically, it would go like that because we do tip to tail, right? So south 800, north 100, south 750, tip to tail. How far do they? Well, the last day about. Drop a diagram of the journey and find the total displacement. So the easy way to do this is going to be seeing how this is all in the y dimension. We're going to have negative 800 and then positive 100 and then negative 750 because it's down 800, up 100, and down 750. And last time I checked with the calculator, negative 800 plus 100 minus 750. You would have a total displacement of negative 1450. And how does that differ from the total distance? It's going to be 100 kilometers less than the total distance because the total distance would be 800 plus 100 plus 750. Again, the distance isn't a vector, it's a scalar. So, yeah, there you go. Second one, seal Tim's towards an inlet at a speed of 5 meters per second as the current flows the opposite direction 1 meter per second. How long would it take the seal to swim 100 meters? So this is actually this is a good question just to sort of think about. So the seal goes that way, let's say 5 meters per second, and the current is going that way, let's say 1 meter per second. So the seal is actually going 4 meters per second. And we want to know how long it'll take the seal to swim 100 meters. Well, he's not going to be going any different speed than 4 meters per second, so we can actually use V equals D over T to figure that answer out. So 4 equals 100 over time, cross multiply 4T equals 100, and divide both sides by 4. 100 divided by 4 would be 25 seconds. So hope that helps. Next. Avery sees this is finally a good two-dimensional problem. Those other two were they were good, but they weren't very difficult. I hope you didn't have to think too hard about them. This is actually finally we're getting into something good. So this is a problem where we're actually going to use our x and y, and I kind of told you during class on Friday, set up an x and a y chart and find the total displacement. So Avery sees the UFO at her bedroom, calls the police. So the UFO moves 20 meters to the east, and that's going to be, if you remember your cardinal directions, never eat soggy waffles, northeast, southwest. So we're going 20 meters to the east. That's going to be positive 20 in the x with nothing in the y. 30 meters west, that's going to be negative 30 meters in the x and nothing in the y. And I'm sorry, 10 meters north. So that'll be 10 meters positive in the y with nothing in the x. And the beauty of this is you can do them in any order you want. So 20, 10, and 30, as long as they're all there. So grand total, this thing will have moved negative 10 in the x and positive 10 in the y, which means it will go that way, 10, and that way, 10. So we want to know the displacement, which is what you get when you add these two vectors together, which is going to be let's try that again. That. So how big is that? We have two sides of a right triangle here, so we can do a squared plus b squared equals c squared. And because we're looking for the displacement, we also need the angle. The beauty of this is they're both 10, so you know the angle is 45 degrees. My hope is that you can recognize that, but that's very convenient. So we could also use inverse tan of 10 over 10 because the opposite is over here, the adjacent's over here, and they're both, 10. And you should end up on your calculator, if you plug that in, 45 degrees. Now, in terms of actually figuring out the how far it went, we're going to have to use a squared b squared equals c squared. So 10 squared plus 10 squared equals 200, and then the square root of 200 is going to be, if I can get my calculator to work, 14.14. So 14.14 meters away. So from here to here, the UFO went 14.14 meters and a direction of 45 degrees, technically north of west, because it went west first and then north. I don't foresee us really throwing any of these at you, but I wanted you guys to really, remember how to do vector resolution and vector addition. It's a very important skill to have, not necessarily for this test, but definitely for what we're going to be doing next when we start looking at forces. Next. All right. Esther dives off, and I can't type, but I don't care. 3-meter springboard and initially bounces up with a velocity of 8 meters per second and angled 80 degrees to the horizontal. What are the horizontal and vertical components? Yeah, I just got in from raking, so my fingers were not really in the mood to type all this stuff out. Hope you don't mind. But you should be able to follow along. So we're looking at the horizontal and vertical components. So Esther goes like this, 8 meters per second, 80 degrees to the horizontal. So we are looking for the vertical and the horizontal. So this is the angle that we're looking at. This is my opposite side, this is my adjacent side, and this is my hypotenuse. To figure out the opposite side, I'm going to be using sine, because sine, just from SOHCAHTOA, sine is given by the opposite in the hypotenuse. Cosine is given by the adjacent in the hypotenuse. Tangent is given by the opposite in the adjacent. So I really, I hope I'm recording. Please tell me I'm recording. Good. Okay. Just wanted to make sure. So yeah, because we're looking for the opposite and we have the hypotenuse already, we're going to use sine of 80 equals the opposite over 8, which is my hypotenuse. And that means we're going to find the opposite side. We'll multiply both sides by 8. So those cancel out. O equals 8 sine 80. And 8 sine 80 is going to be 7.87 meters per second. And for the adjacent side, we're actually going to use cosine because that has the adjacent. That will give us the adjacent if we have the hypotenuse. Cosine of 80 equals adjacent over hypotenuse, which is 8. Again, multiply both sides by the hypotenuse. 8 cosine 80 is going to be the adjacent side. 8 cosine 80. And just make sure your calculators are in degree mode, and you should end up with 1.389, which I would round up to 1.4 meters per second. Cool. So I hope that's not too much of a surprise. Moving on, in many locations and old abandoned stone quarries have become filled with, oh boy, I really got sloppy typing. Filled with water, once excavating has been completed, while standing on a 10-meter high quarry wall, Clarence tosses a piece of granite into the water below. If Clarence throws the rock horizontally with a velocity of 3 meters per second, how far out from the edge of the cliff will it hit the water? So we have a cliff problem. Literally, we are standing on a cliff. So we should probably make our XY chart. VI, VF, ATD. Let's see, what do we know here? Without even thinking, 0, negative 9.8, and seeing as it's a cliff problem, it's going to be 0. Clarence throws the rock horizontally with a velocity of 3 meters per second. How far out from the edge of the cliff will it land? So we're looking for this. And the one more thing we need, 10 meters. So this rock is going to go negative 10 meters down. So as we've done, d equals VIT plus 1/2 AT squared. Negative 10 equals, this is all going to be 0 because the initial velocity in the y is 0. This is all y stuff, by the way. Okay. Negative 10 equals 0 times the time, which we don't know, plus 1/2 negative 9.8 times squared, which we don't know. So this is all going to go to 0. So negative 10 equals 1/2 times negative 9.8 is negative 4.9 t squared, and then we have to divide both sides by negative 4.9. We should end up with t squared equals divided by negative 4.9. That should be 2.04, and then square root of that, because we want t. T is going to be, oh boy, fancy pants calculator, square root of 2.04, 1.42 seconds. So that's a start. Now you might say, Mr. D, why do we find time? And the answer is because we can't do anything without time. So we know it's going to take 1.42 seconds for it to hit the cliff or the water. And now that I've got a time, I can use V equals d over t. So now I can look at my x stuff, and that's going to be v equals d over t. 3 equals d over 1.42. So actually it's probably 1.43 if you really round it right, but 1.42 times 3 is going to be 4.26 meters, and there's no way I can fit that in there. 4.26 meters away. All right, so with cliff problems, use your y stuff to find the time, and then get your x stuff. Let's give another one. While skiing, Ellen encounters an unexpected icy bump, which she leaves horizontally 12 meters per second. How far out horizontally will Ellen land if she drops 7 meters from the fall? It's exactly the same thing we just did. X, Y, V, I, V, F, A, T, D. We know the velocity in the x is 12, the final is 12 because the acceleration is 0. And we know that's going to be negative 9.8. We also know she falls 7 meters, so that's going to be negative 7, and she goes horizontally off of this thing, so that's going to be 0. So again, we got to find the time, because the time is what's going to be the same for the x and the y, and then we can figure out that displacement, and hopefully I can fit it in there. So, d equals VIT plus 1/2 AT squared. Displacement is going to be negative 7 equals VI, which is 0 times t plus 1/2 negative 9.8 t squared. Negative 7 equals 0, because that's all 0, plus 1/2, well actually, here I'll do a little bit of the math now. 1/2 times 0 plus half of negative 9.8 is negative 4.9 t squared, but we know that that 0 times plus anything is 0. So negative 7 equals negative 4.9 t squared. Divide both sides by negative 4.9. Divide by negative 4.9. Those will go away. We're left with t squared equals negative 7 divided by negative 4.9. We should end up with 1.42. And then we don't want t squared, we want t. So t is going to be the square root of 1.428. 1.19, I just rounded 1.2 seconds is our time. 1.2 seconds is our time. And now I can do, again, I can look at my x stuff. V equals d over t. And let's see here, with the x, I got 12 equals d over 1.2. 1.2 times 12 is 14.4. And that means our poor skier will go 14.4 meters horizontally out from where he made the fall thing off the bump. Okay, hope that helped. Hope you got that right. And if you didn't, I hope you get it now. I mean, there's really, this is pretty much what it's going to look like on Monday. Essex County Sheriff is trying to determine the speed of a car that slid off a small bridge on a narrow New England night and landed, or on a snowy New England night and landed in a snow pile 4 meters below below the level of the road. Tire tracks show the car landed 12 meters horizontally from the bridge. How fast is the car going when it left the road? Another cliff problem. I mean, we've got a bridge, and then the car went off the bridge and landed 12 meters away. So now it is a cliff problem, but it's not a typical cliff problem. VI, VF, A, T, D. It's actually a little bit easier than a typical cliff problem. So we know a couple of things. We know some distances, which is really important. First off, it skid off a small bridge, so that means it didn't go like jumping into the air. So again, the initial velocity in the y is 0. We're actually trying to figure out the velocities in the x. And we know the accelerations are 0 and negative 9.8. We know the displacements. So 4 meters below, so we know that is negative 4. And we also know the car landed 12 meters away horizontally from the bridge. So this is a big deal. Again, we're going to use x and y stuff, or I'm sorry, we're going to use the y to find the time, and then we're going to be able to go back and calculate the velocity. So let's do that. All right. Again, I've got a D, a VI, and A, so I can do D equals VIT plus 1/2 AT squared. Negative 4 equals, this is going to be 0 plus negative 4.9 T squared. It's 1/2 of negative 9.8. Again, this is all Y stuff. So negative 4, this is going to go away because it's 0 plus. So let's see, negative 4, we're going to divide both sides by negative 4.9. Negative 4 divided by negative 4.9. It's going to be 0.816. So t squared is going to be 0.816. And then we're going to take the square root of that because we want not this t squared, we want t. So t is 0.9, I'm just going to leave it at 0.90. It's 0.90, blah, blah, blah. But let's make it easy for ourselves. So 0.90 is our seconds. Now I can go ahead and plug this back into what I used for the x. So v equals d over t. V is what we're looking for. D is 12. T is 0.9. So 12 divided by 0.9 should be 13 1/3. 13 1/3 meters per second. So that equates out to a little over 30 miles an hour. But there you go. Hope that helped. Next. Superman is said to be able to leap tall buildings in a single bound. How high a building could Superman jump over if he were to leave the ground with a speed of 60 meters per second and an angle of 75 degrees to the horizontal? This is a little tricky. And the reason is we want to know how high the building is that he could leap over, which means if this is the building, we have to look at, all right, he's going to jump and go like this, and we have to remember how fast he's going at the top. So we're actually going to have to do a couple of things, and we're not going to look at the whole trip. We're going to look at half of the trip. All right? So it kind of goes against most of the ones that we've done, but logically it should make a lot of sense. A, T, D. We know this is 0. This is negative 9.8. The VI and the VF and the Y will not be the same on this because, again, we're only looking at half of the trip. So now I want to know what the initial velocities are. Well, they give me 60, and you should remember that 60 goes nowhere. 60 is my hypotenuse, and 75 degrees is the angle. So we have to figure out the opposite side and the adjacent side. And from the first couple of problems we did, we need to remember that this is just going to end up being 60 sine 75, and this is going to be 60 cosine 75. 60 sine 75 is 57.95, and 60 cosine 75 is 15.52. So I'm going to go ahead and put those here. 57.95 in the y because that's the opposite, that's the going up side, and 15.52 goes in the x. And we have to remember a couple of things. This is also going to be 15.52. Now typically if we were looking at how far he would go, we would put negative 57.95. So if we were to extend this out and say, well, how far could he, how far away could he land, like over here? Then we'd look at negative 57.95 and get the whole time. But we don't care about the displacement in the x, we actually care about the displacement in the y. And to do that, we have to look at how high he can go when he stops going up. And that is why, my friends, we are going to put the number 0, if I could make my... I want you work. Oh boy. That was awkward. Anyway, so yeah, somehow my pen stopped working on here. So again, we're looking at how high he gets to go, which means we have to look at how far he goes when his when his velocity in the y dimension becomes 0. So that's why I'm going to plug in a 0 right there. So the good news is this actually allows us to use a very easy equation. Instead of d equals vit plus 1/2 at squared, we're going to use all of our y stuff. So we don't even care about the x. We're going to use vf equals vi plus at, and that'll get me the time. Or I could even just save myself the aggravation of finding the time and then finding the displacement. I could actually use vf squared equals vi squared plus 2ad and get my displacement that way. And then I don't even have to worry about time. And that's actually what I'm going to do. So vf squared, 0 squared is 0. Vi squared, 57.95 squared, is going to be 3358 plus 2 times negative 9.8 d. So now I got to get 3358 over to the other side. So I'm going to subtract that from both sides. 3358 equals negative 2 times, I'm sorry, not negative 2. 2 times negative 9.8 d. Then 2 times negative 9.8, 3358 equals 2 times negative 9.8. Negative 19.6, 19.6d, and then I'm going to divide both sides by negative 19.6, negative 19.6, so 3358 divided by negative 19.6. Well, the good news is those two negatives will cancel out, and I will end up with a displacement that is positive, because Superman's going up, 171.3 meters, give or take. So there you go with that. And that's good because we're looking for displacement in the y. How high can he go? Now, if we were looking for displacement in the x, how far could he go? That's when we're going to go ahead and do the negative 57.95, and then we do vf equals vi plus at, find the time, and then plug that back into my x stuff. So I hope the logic of something like this makes sense. You know, it's just another way to kind of look at our normal two-dimensional kinematics problems. And that brings us to our last one, which this you really have to put your thinking cap on. Lenny's running to school and leaping over puddles as he goes. From the edge of a 1.5 meter long puddle, Lenny jumps 0.2 meters high off the ground with a horizontal velocity component of 3 meters per second in an attempt to clear it. Determine if Len sits all day in wet school socks. Okay, so this is going to be, again, XY, VI, VF, ATD. I don't anticipate something this, well, I don't know. I think this is a little over a B problem. I think it's a little under an A problem, but you know, maybe we're going to go through it. So first and foremost, we want to see if he clears 1.5 meters. So we need to solve for D in the Y. I'm sorry, D in the X. So we need to solve for D in the X. Not put 1.5 meters in there. All right, we want to see if D in the X is bigger than 1.5. We know he jumps 0.2 meters up, but we also know that 0.2 meters up is only half of the time. So if we figure out this time, we're going to actually have to sort of double it to get back to how far he actually goes. With the horizontal velocity, he's got a 3 meter per second horizontal velocity. So here's the basic story. There really isn't a lot of information here for us to look at until we remember our physics. So this is what the problem gives us. Remembering our physics, we know acceleration is 0, and that's negative 9.8. And then we have to remember this, right there. At 0.2 meters high, he has stopped in the y dimension. He's still going 3 meters per second in the x dimension, but he's stopped in the y. So now, in order to figure out time, I don't have enough information in the x, but I have it in the y, if I figure out the initial velocity. So I don't have an equation right now that's got a VF, an A, a T, and a D. That equation doesn't exist. But if I can figure out the initial velocity, then I can figure out the time, and then I can go to work on the X side. So for you, I hope you realize we can use VF squared equals VI squared plus 2AD. That would be the way I would go. VF squared equals VI squared plus 2AD. So far, so good. So that's going to be 0 squared equals VI squared plus 2 times negative 9.8. 9.8 times 0.2, because that's our D. Now, this is all one constant. So I'm just going to plug that all in. 2 times negative 9.8 times 0.2. 2 times negative 9.8 times 0.2, not negative 2. So we're going to end up with 0 equals VI squared plus a negative 3.92. We're going to add 3.92 to both sides. And then we will end up with that canceling out. We will have VI squared equals 3.92. And we don't want VI squared, we want VI. So we're going to take the square root. Square root of 3.92 is 1.97. So now I know my initial velocity is 1.97. Now, we can do two things, and I'm going to actually sort of go back on what I said in the beginning of this thing. We could find time and double it, and that might be easier, but now we actually have a normal up and down, what's the range, what's the distance he goes in the x dimension problem. So you know what I'm going to do? I'm going to change this chart. I'm going to take this, I'm going to say, all right, look, Lenny goes up 1.9 meters per second. Lenny must then come back down with a negative 1.97 meters per second. And if that's the case, he no longer goes 0.2 meters up. He comes back down to the ground, which is 0 meters. So in the interest of space, I'm doing this on the same chart. I totally invite you to make a separate chart. Okay? But now that I have this, I can use the old VF equals VI plus AT. Negative 1.97 equals 1.97 plus negative 9.8t. And then negative 1.97 minus 1.97. I subtract 1.97 from both sides. So those go away, and I'm left with negative 3.94 equals negative 9.8t. And then I'm going to divide both sides by negative 9.8. Those go away. I'm left with t equals negative 3.94 divided by negative 9.8. I should end up with a time of 0.402 seconds. Now, this is all about how far does he go in the x dimension. I now have enough information to figure out how far Lenny goes in the x dimension using b equals d over t. 3 equals d over 0.402. We're going to multiply both sides by 0.402. d 0.402 times 3 is 1.206. So that's how far Lenny can jump. How far is the puddle? Is the question. The puddle is 1.5 meters long. Lenny jumps 1.206 meters. Lenny has wet socks. Boo-hoo. Lenny is sad. All right. I hope that helped. This particular problem is tough for the first piece of it. Once you're here, once you've got a positive 1.97 and a negative 1.97, I hope it was a little easier, just to figure out the range, how far Lenny goes. And that's it. If you have any other questions, shoot me an email. I'll be in probably about 7:05 on Monday. And if you need any help, I can help you out with those. I hope this review sheet was good, and I hope this video helps you guys out.